on your weekly schedule, you should see your notes for for this week, and you should also kind of see our plan for this week. So we are going to do a little activity today, and then just like we did last week. And then we're going to do a little activity on Wednesday, and then a little activity on Friday, a little quiz on Friday. Okay. So if you look on they're in the Teams app, but if you look on the weekly schedule, it says like session recording will be here. That's where I'll put the recording on. So, and if you go back to last week, I already have last week. All right, so what was I saying? Oh, so just like last week, we are going to be doing notes activity on Monday, notes activity on Wednesday. If you are in a dual credit class on Tuesday, Thursday, again, you're expected to be with your teachers, okay, until your class time starts. So, for example, let's say you have a class at 10 o'clock. That doesn't mean you get to miss my class for 20 minutes and then go to your 10 o'clock class. So, you need to be with me until 10 o'clock and then leave. So, every minute of the day, you're with a teacher at somewhere, okay? But when your dual credit class starts, then you can leave the class and go somewhere. On Tuesday, Thursday, there is a little professional habits assignment in there. Those of you with dual credit that are missing the class, I will exempt you from those professional habits. However, that exemption means that it won't hurt your grade, but it also means it won't help your grade. So if you look at the assignment and you're like, I could do that really quick and I could get a good grade on that, go ahead and do that assignment, even though you are excused from it. Okay, so again, that's going to be dual credit kids that are missing my class on Tuesday, Thursdays. You will be exempted from doing the professional habits, but you can still do them if you want. Okay. So again, professional habits is 30% of your final grade for your classes. So, something. So, well, it can't. Well, if it stays exempted, it doesn't hurt. Or it doesn't help. It doesn't hurt. But if you do it, you get an A, and it helps. So that's what I'm saying. If you don't do it, it's exempted. It doesn't help, doesn't hurt. But if you do it, it could help your grade. So if you want to improve your grade and you have time, especially this week, you'll see on weekly schedule. This week literally takes you 60 seconds. You read your instructions and do the activity. Just do a good job with it. Okay, anyways, let's do our notes for today. So again, you guys will be pulling up a note to call fission and fusion note. And we're going to talk a little about nuclear reaction. So let me pop that up real quick. Start recording. Yep, we're good. All right. Fission and fusion notes. I'll put you guys on the screen over here. All right, I'm gonna put you guys over here. All right. So if I keep looking over there, that's where you are. All right. So today we're gonna talk about fission and fusion notes. And again, you have these. I would so this class ends at 10:25. So you'll miss pretty much all of it. No, you won't see me at all. All right. So today we're going to go over some fission and fusion notes. Again, you have this document. I encourage you to make notes. I encourage you to make your own copies. I encourage you to have paper and pencil and a notebook to write things down. I'm going to say more than what's on the screen. I encourage you to, think about that. Jotting down some stuff as we go over nuclear fusion and fission. So just a reminder, there will be a weekly quiz on Friday, just like it was last time. Get information from the PowerPoint, information from any activities that we do, which we're going to do on today, information from any question and answer session. The quiz is going to be unlocked Friday morning and locked back up. Okay. When you guys look at the assignments, it should tell you what time they open and lock. So be mindful that if you see that something closes at 10 a.m., don't wait till 9:50 to do it. Okay, you might not have enough time to finish it. Okay, so just be mindful of that, making sure you plan out your day, plan out your attack a little bit. Okay, Again, we're going to have time to do it in class on Friday. All right, so today we're 3 through 12. Everybody else hear me okay? Hopefully it sounds a little better, but today we're just going through the notes. So you guys have the notes, just kind of follow along with me on here. So nuclear fission, we're going to do slides 3 through 12 today. And so we talked about types of radiation last week, talked about alpha, beta, gamma radiation. Gamma radiation is just pure energy, and it's a really small electromagnetic radiation. It's a wave, and it just literally goes right through your body. It goes through your body, through your cells, and can damage your DNA as it travels through your cells. Neutron, we haven't really about it, but neutron is essentially another particle that can be lost. So an alpha particle is the helium particle with 2 protons, 2 neutrons. A beta particle is an electron all by itself. Gamma radiation is just energy, and the neutron is a particle that we all know of, has mass of 1 but does not have a charge at all. And so for the gamma radiation, a little bit more in depth from what we were talking about last time, is that remember that gamma radiation, we write it down as like a Y, and that's a Greek letter for gamma. It looks like a G, but the Greek letter for G is a Y looking thing, but it's called a gamma. It had no mass and it had no charge, so it's a 0, 0. It's not a piece of matter, it's just energy. And if you look on there, it says 60 centimeters of aluminum or 7 centimeters of lead. That is the ability to penetrate through that. You are not made of metal at all, so that gamma radiation can go right through you really easy. There's a much greater risk to health than compared to alpha and beta. The good news is that you're not going to be exposed to gamma radiation very often. The bad news is that if you are exposed to gamma radiation, it doesn't take a lot to quickly hurt you. Okay? So protection from gamma radiation. For us here, the protection that we'll need to do is either wear lead equipment, like a vest or something like that. But even then, you're not going to protect yourself very much from gamma radiation. Is to get underground, and even in a concrete or lead-lined bunker or something like that to protect you from gamma radiation. Gamma radiation is pretty bad. So when you do like experiments with it in college and things like that, but sometimes college will do that, they will be in a major metal lead enclosed container so that it's as safe as possible. Okay. And again, it's just pure energy. There's really nothing that we can do to protect ourselves from it. The very first thing you'll notice if you're exposed to gamma radiation, I think I said this last week, but you'll notice that your vision starts to kind of flicker and starts to go away. The gamma radiation, as it penetrates your eyes, will cause your eye cells to die off and break down. And so your vision will be one of the first things that goes, and that's kind of how you know you're exposed to radiation. You're not really going to feel it any other way. I mean, you're not going to feel the particles going through you, but you can kind of see them. You can kind of notice it in your eyes. So if you start all of a sudden losing vision, probably what it is, probably some kind of radiation poisoning. But then, of course, as it travels through your body, it can poke little tiny holes and everything. There's a lot of internal bleeding, a lot of hemorrhaging, especially around the brain, and you can die pretty quickly from gamma radiation. It is not going to turn you into a big green monster with big muscles. Okay, unfortunately. If you're exposed to just a little bit of radiation, absolutely nothing can happen at all. You can, not like it's guaranteed to kill you or anything. But one of the dangerous parts about gamma radiation is, and again, I said this last week, is that it could kill your sex cells, your gametes, or it could damage your sex cells. But you're fine. You're perfectly fine. You'll live a nice long life. But when you go to try to have kids, your sex cells, your gametes might be damaged, and it might have difficulty having children because of that. But again, you as a person, you're perfectly fine. You can damage lots of cells in your body. You have trillions upon trillions upon trillions of them, but Again, you don't want to damage your sex cells when you try to have kids. All right, I see a hand up real quick. If you would. Jace, you got a question?
Do you know what's the highest amount of radiation someone survived?
Survive?
Yeah.
Um, I would have to guess probably somebody from Chernobyl. Um, there were people when Chernobyl happened. There were people that went into the reactor to clean it and stop it from reacting. Some of them are still alive. Most of them died from cancer later in life. I think Chernobyl officially killed like 10 people immediately from radiation. But then, of course, the numbers are like a million people are affected by it later in life. But I would have to imagine it's probably someone from Chernobyl. I don't know the exact number, but radiation part of our everyday life. Um, there was a guy I know that. Yeah, he lived in Nagasaki, worked in Hiroshima. When he got bombed in Hiroshima, went back home in Nagasaki and got it again, or vice versa, one of those. But yeah, I don't know the actual behind that. So yeah, yeah. And then of course, same thing for Japan. You know, a lot of people died immediately. I think they said something like 30,000 died, but millions of people later in life. You know, so radiation sticks around for a really long time. All right, so in the gamma decay, we talked about this already. There's no change in atomic mass or atomic number. It's just energy from within the nucleus. That's all that changes. So neutron has a mass of 1 and atomic and no proton, no charge. So we say that neutron has a mass of 1 at top and a 0 for an N. And again, a neutron can also be emitted, just like the proton, neutron, electrons. You know, it's in there. Because it's not a charged matter, it doesn't ionize matter. They can travel a lot farther through particles, and again, they're really small. But again, they're not really interacting a whole lot with the matter, so it's not really that, you know, there's not really a super big deal there. But what can happen though is the neutron being a somewhat of a bigger particle, as it travels through the atom, it can knock off electrons, and those electrons can leave and do stuff. But again, it's not really the end of the world for that. And so neutrons actually can kind of go through the most material, but again, not quite as bad as we're looking for, like for gamma radiation. All right, so nuclear forces. So remember, we talked about proton, neutron being stuck in the nucleus. The nucleus is a bunch of protons together. They're all positively charged. They don't want to be together. They want to repel each other. Remember, opposites attract, same repel. So in order to put all the protons together, you need neutrons to hold them together. And it's like a gravitational force where you're forcing them together used by mass, but we call it a strong nuclear force. So there is a force holding the protons and the neutrons together. Okay, and so you're looking for a ratio of proton to neutron that makes it stable. If you have too many protons, too many neutrons, the atom just becomes unstable and it can break apart or decay. And we call that the nuclear force. So it's called a strong nuclear force, and this is the force that holds proton and neutron together. Um, and it is stronger than the force of repulsion from the proton. However, if you get too many protons to be next to each other, it doesn't matter how much, how many neutrons you have, they just can't stay together. So right now, element number 93 and above, we put 93 protons together. Doesn't matter how many neutrons you have, they're unstable. They can't put that many together. Okay? So uranium number 92 is the last naturally occurring isotope on Earth because it's stable kind of at 92, but you take away a couple of neutrons and it's not stable at all. So you take away 3 neutrons from uranium, and then you get yourself the material, what we call enriched uranium, get a material for nuclear power, nuclear weapon, things like that. And it's not easy to do, so don't think that you can just make enriched uranium. It's difficult to do. It took America like 10 years, or I think it was like 4 or 5 years, just to make enough to make the atomic bomb later. Right, fusion. So today we're talking about fusion. So fusion is a process of combining. You're going to fuse together. You're going to combine nuclei together at extremely high temperatures and force, and that is going to create a larger atom or larger nuclei. Okay, so you're going to take two little ones and push them together to make a larger element. That's how large elements are made. Large elements are made from smaller elements. You just combine them together. Okay, and the thing that makes that happen are stars. So stars force atoms together, or other massive explosions in the universe called supernovas. They force atoms to come together. So our sun is producing element helium through oxygen by putting hydrogen together. It smashes a bunch of hydrogen together, put hydrogen together, helium together, put lithium together. It's smashing those atoms together to make larger atoms. Our sun is not really a big star, so it can't make a bunch of elements. Stars can make elements all the way up to number 26, which is iron. And then after that, after iron, all those elements are made up from stars exploding in supernovas. And that's what forcing those atoms together. So we're all basically star matter, because stars are the only thing big enough to force atoms to come together. Earth is not doing that. Earth is not forcing atoms together in nuclear fusion. Humans, we can do that. Um, we're not great at it, but we can do that and make nuclear fusion as well. So you see there's a formula down here. And again, you're just combining two atoms. All you're doing is adding the masses on top and adding the masses on bottom in order to balance out the equation. Okay. So if you have neon and helium, looking at the periodic table, that's 10 plus 2, it can make magnesium. Again, look at the periodic table, magnesium is 24. Okay, so neon 21 plus 4. Wait a minute, that doesn't add up. So I need to add a neutron in order to make it add up. Or I need to add an electron to add it up, which that won't happen. But you can add other particles to make the equation balance out. So nuclear fusion, again, essentially what's happening here in solar energy is when you put the two together, it's going to release light, heat, and radiation energy. Actually, fusing them together creates energy. Okay, so it says 1 pound of helium here can release 16 million pounds of burning coal. So trying to convert energy into nuclear fusion and is really what scientists are trying to do right now. The nuclear fusion energy is actually really, really efficient compared to coal and wood and things like that. However, it's very difficult to produce, and so therefore it requires too much energy to make the material for nuclear fusion. Therefore, it's kind of we're losing energy in the process, so it's not very efficient for us right now. But we're working on it. We're working on trying to get better nuclear fusion. And ultimately, the best idea would be cold fusion. Cold fusion is where it does not require as much energy to form them together, then that releases energy. So if we can figure out a way to put the atoms together easier so that they can release energy for us to use for electricity, that's what we're looking for when we talk about cold fusion. Probably not going to happen. It's kind of a theoretical thing, but that's if you can do that, you can have unlimited electricity for free, basically. And so it probably won't happen. All right, so fusion. So the pros of fusion energy is that hydrogen is abundant, especially in the universe and especially on Earth. The con, though, is that it's highly energetic and dangerous, but we don't have the materials to easily make it for nuclear fusion. And also any shielding material that you use with that radiation will have to be replaced often because of the radiation that's involved with that process. All right, so today we're going to take a look at nuclear fusion today. So if you go to your weekly schedule, there's an activity that says nuclear fusion part A, fusion. You guys are going to need to grab this worksheet, make a copy of it. So again, it's a gizmo. I know we do a lot of gizmos, but they're kind of our hands-on learning, especially doing nuclear chemistry. Not a lot of hands-on we can do. So when you go to the gizmo, there's going to be a couple of things that you need to set up. Okay, so very first thing you want to do is click on reset. This is the same gizmo we did last week, but this time we're going to do a proton, but then we're going to see kind of what happens here. Okay, and so this one here said all stars turn hydrogen into helium. Process called fusion. Stars perform this a different way, like our sun. It's called the proton-proton chain. So you're going to add protons to different things, and it also requires a really high temperature. So this is what we're going to start with. So if I reset everything, make sure we're on proton-proton. So proton-proton is what's going to make the atom bigger. We're going to start with 1, then go 2, then go 3, and then go to 4. So if I fire off a helium at this proton, helium with 2 protons, note that nothing happened. Nothing happened. Didn't do anything. So firing off a helium, that's not the right step. So it's not proton plus helium. Maybe we can fire off a neutron. Okay, that didn't happen. That didn't work, right? So that's not the right step. So maybe we fire off a proton. Oh, what happened? Did you guys see what happened there? What did the proton turn into?
A neutron.
It turned into a neutron, right? So remember, the protons don't want to, right? They don't want to be next to each other. They're going to repel each other. So what it does is that repulsion is that it gets rid of the energy. Like, hey, take the energy. We'll turn it into a neutron. Neutron makes me happy. Okay. All right. So that's the next step. Watch what happens to the equation now. When I hit next, the equation changes. Okay. Because now I have a mass of 2, but I'm still hydrogen. I still only have 1 proton. So let's see. Let's fire a helium. All right. That didn't work. Fire another neutron. See if anything happens. Okay. That didn't work. All right. Fire another neutron. Proton. Oh, this time it did not change. It did not change into a neutron, but it did release energy because the neutron is holding the proton together now. Okay, and that's draw nuclear force. Again, watch what happens to the equation. Now we have a different atom. Okay, now we have helium, 2 proton, but it has a mass of 3 with that neutron there. Note that we now have a different equation. Okay, and so this is how we're going to do it. Let's say a fire helium. Anything going to happen? Oh. Something happened, right? What if we fire off, okay, well, that was it. So that was the last thing I could do on that one. So let's make this a little bit quicker here. So there are lots of little things that we can do in this chain here in order to make other atoms. And just keep firing protons in here, kind of see, okay, that didn't work. Let's fire a neutron. Okay, neutron did work. All right, notice what happened though. A neutron. Okay. So we can keep changing these guys here and then keep going from there and kind of seeing how we can make larger and larger atoms from there. Okay. All right. So that's going to be your process for today. And again, remember, you guys can type in these boxes in order to make the equation work. So I don't remember. So let's do a reset. So we needed to add a proton first, right? So you guys can type in proton has a mass of 1p. You guys can actually add all those in. Then we need to add another proton. Okay. And then, so this is just going to keep changing your equation into nuclear reaction. All right, I'm going to do breakout group. Let you guys work together for about 10, 12 minutes. Help each other out. Remember, when we are in breakout group, talk to each other. Be friendly. Have fun with your classmates. Don't just sit there like a bump on the log. But then if you guys have questions, talk to each other. If you guys can't answer the question, put them in the chat box. I'll come in and jump into your group. So, all right, let's do this. Do 5 rooms. And I'm going to go ahead and stop the recording because it doesn't record breakout group. So hopefully that everything that we did on there makes sense.